Hello, everyone. This is the E1 lecture, which is the introduction to cladding principles and the rain screen system. So this is the beginning of the final series of lectures with the E prefixes on the lecture handouts that are on UB Box. When we talked earlier in the semester about masonry and wood systems, we saw how these evolved from solid monolithic construction systems to systems that we use today, which are assemblies of thinner layers. And so in masonry construction, we compared the traditional solid brick walls, which you see on the left, to the more recent development of the layered cavity wall. Likewise, in wood construction, the evolution has been from solid log walls to first to heavy timber framing and now to the light wood or platform frame with its thin layers of cladding both inside and out. And so most construction, both small and large buildings, is now this assemblage of thin layers. And so this affects the nature of labor on the building site. Historically, buildings would have been constructed by small crews of workmen with a range of skills, and the same crew would have been on the site from the beginning to the completion of the project. Now, a building is built by many different trades, many different subcontractors. And so there might be separate crews on the site for building the foundations, for doing the rough framing, installing plumbing, electrical services, and HVAC services, uh, roofers, exterior finishes, interior finishes, millwork, etc. And on large buildings, this is even more pronounced. Every layer of construction has a specific role and it's done by a separate subcontractor. There are rules to these systems, and as we saw with Frank Gehry and the Spiller House, there are ways of reinterpreting or challenging the rules that govern how the layers are assembled. You, as an architect, will be responsible for coordinating the trades as you develop the construction drawings in for your building and keeping the total picture in your mind of the building. So we should be thinking about this as we begin this series of lectures on enclosure systems or the exterior cladding of roofs and walls. So we will start by considering some general principles about cladding. What do we mean by the term cladding? It is the exterior layer of finish of the building. It is the envelope system. It is often called the building skin. And the functions of the exterior cladding are twofold. The first is to determine the exterior appearance of the building, and the second is uh, a number of environmental roles that the building skin performs. The cladding of the building is an environmental mediator. It keeps water and wind out. It contributes to the insulation performance of the building, and it may provide sun screening or sun shading, for example. In the past, these functions were accomplished with a thick monolithic construction. Now there are many layers. So our concern in today's lecture is primarily how the building cladding keeps water out, and we'll be talking about water in liquid form and water in vapor form, principally about water in liquid form, and 2, how cladding determines the exterior appearance of a building. In order for leaks to occur, 3 things have to happen simultaneously. And this is covered very well in your textbook. The pages are noted on the semester schedule. And these 3 things are very useful to keep in mind for any kind of cladding system. So the 3 conditions that have to occur for a leak to present itself are, number 1, that water has to be present in solid, liquid, or vapor form. 2, there has to be an opening for the water to move through. And 3, there has to be a force to push or pull the water through the opening. All of these have to be present at the same time. If any one of them is not present, then no leak occurs. Therefore, there are 3 conceptual approaches to making a building watertight. Each approach seeks to eliminate one of the above conditions to prevent a leak. So let's consider each one. Approach 1 would be to try to eliminate the presence of water. But water is everywhere, in solid, liquid, and vapor form. It is 2/3 of the Earth's surface and a large percentage of the tissue of living organisms, including our own bodies. So it is therefore impossible to eliminate the presence of water. Approach 2 is to eliminate the opening for water to move through. And this is the basic principle of most of the long history of buildings, where builders have tried to make the exterior cladding a sealed system. On your lecture handout, this is referred to as the face sealed system, meaning on the outer face of the building, sealed, so that water cannot get through. If all of the joints on the outer face of the building are sealed, the idea is that there is no opening for water to get into the building. The problem with this approach or assumption is that, number 1, it's difficult to design a completely sealed system. But let's suppose for the moment that we could. The second problem is that it's very difficult to build a completely sealed system. That is, to build a perfect system with perfect materials and perfect workmanship in every joint. The likelihood of achieving this is virtually 0. It might be possible to get a perfect building in a laboratory setting, but if you think of how buildings are built, what the building site is like, how many people are involved, how complex the process is, not to mention the weather, the likelihood of perfection on the site is 0. And finally, the third problem is that it is difficult to get materials and systems to perform perfectly day after day, year after year. If you think about our climate in New York, which ranges from very hot to very cold, sometimes within the time frame of a few hours, not to mention seasonal extremes, you understand the heavy wear and tear that weathering causes to buildings. So again, it is virtually impossible for buildings to perform perfectly day after day, year after year. So this approach to preventing leaks by trying to completely seal the building envelope is fundamentally flawed. However, human beings have worked with this approach over the centuries because it seems so obviously the best and only way to proceed. Approach number 3 is to eliminate the forces moving water through openings. And again, this diagram is from your textbook, and so you can refer to it there. There are 5 different forces that we have to deal with when thinking about how to detail buildings. The 5 forces are pictured here. We'll look at each of these more closely. So the first force on the left is gravity. And it's obvious that water will move down a slope. So when we design our cladding system, or indeed all of the details of our building, we want to ensure that water moves down and out of the building, not down and into the building. And so this is common sense. This is why roofs are sloped. This is why windowsills are sloped and louver blades are sloped. And this is why we slope the ground down and away around the foundation of our building. The second force we need to deal with is momentum or kinetic energy. So water droplets in motion heading towards a wall have momentum, which is a horizontal component of energy. And momentum can carry the water through an opening. So this can be neutralized by covering the joint, or by making the joint a labyrinth, which you see on the right, which blocks the passage of the water through the wall. So the joint that you see on the right is the shiplap cladding that we talked about when we looked at the Berkowitz house. The third force that we need to deal with is surface tension. And this is what enables water to hang on to the underside of a surface. And this can be resolved by incorporating what's called a drip or a groove into the underside of a surface. So the top surface of a windowsill slopes down and out to deal with gravity. And if you run your hand along the underside of a windowsill, you will usually find that there's a groove in that sill, which is the drip, which prevents water from pulling itself on the underside of the surface into the building. The fourth force that we deal with is capillary action. So an easy way to understand this is if you have a dry sponge and you you submerge a corner of it in water, soon the entire sponge will be wet. And that's because water has pulled itself through the openings of the sponge by capillary action. So capillary action can be prevented by making a break that is bigger than a drop of water, so that water cannot pull itself through. And so what you see in the image on the right, the correct way of doing this is an example of a capillary break. We also talked about capillary breaks at a larger scale when we talked about the cavity wall and the airspace of the cavity wall. The fifth force that we need to deal with is air pressure, and in particular, air pressure differential. Air pressure differential is everywhere, all the time, and it is the most difficult force to deal with. So we could, for example, be talking about wind, but even without wind, there are always differences of air pressure on different faces of the wall. Warm air carries more moisture than cool air, and so the air pressure with more moisture will be greater, and the air always wants to equalize its pressure on both sides of the wall. So differential air pressure exists everywhere all the time. And when it comes to pushing water through the wall, it's a difficult force to counteract. Even with a very small hole in the wall, if water vapor is present, and it always is, the air will want to move through that hole and will take the water vapor with it. So this is true of either water vapor or liquid water, this equalization issue. So therefore, while the principle of the past 2,000 years of architecture has been to try to make completely sealed building envelopes, a recent development has taken a different approach to keeping water out of buildings, which is the rain screen cladding principle that you see on the right. So this works on the basis of eliminating the air pressure differential, the force that pushes or pulls water through holes, and is a good strategy for preventing leaks. So the rain screen system is, and it can be used on either walls or roofs, is a 3-layer system of weatherproofing, and it is based on the following assumptions. It accepts the fact that water is present. It accepts the fact that joints in the building's cladding cannot be completely, totally, perfectly sealed, and therefore it uses open joints. And it tries to decrease the amount of pressure of water present at the waterproof layer, and it tries to minimize the air pressure differential. So this is referred to on your lecture handouts as the 1.5 inches of microclimate. And in this 1.5 inches are 3 layers of cladding that make up the rain screen system. So if we look at the diagram in the right-hand image, we're going to start at the exterior of the building on the left-hand side of this drawing, where the blue arrows are. This is the outer layer, and this is the rain screen. It is open jointed, so you can see the gap between the cladding panels. And the purpose of the rain screen, as its name implies, is to shed most of the water. So let's say that the rain screen sheds 99% of the water. The second layer, where you see the yellow arrows, is the air cavity. And this is an air pressure equalization chamber. The air will pass through the rain screen. The air pressure will equalize on both sides of the rain screen, and therefore the air pressure differential force will be greatly diminished. The third layer of the rain screen system is the inner waterproof sealed layer. So the red dashed line here is the waterproof membrane. And so what's happened here is that 99% of the water has been shed by the rain screen outer layer. The air pressure has been equalized by the air pressure equalization chamber. So by the time we get to the waterproof membrane, there's very little water present and very little air pressure differential to cause a leak. So the outer most layer, the rain screen, determines the appearance of the building. It keeps most of the water out. It is open jointed so the air pressure can equalize on both sides of the rain screen. And the rain screen protects the waterproof membrane, which is where the red dashed line is, from direct exposure to the weather and from direct exposure to ultraviolet light, which causes great damage to building materials over time. The inner layer then is the sealed backup wall. And now this is having to deal with, let's say, theoretically, only 1% of the water present and almost no air pressure differential. So with this system, the likelihood of a leak is much reduced. So just to say that this waterproof membrane is not the vapor barrier. And so if you have the vapor barrier is dealing with moisture coming from inside the building trying to get out. So a vapor barrier is still required, and the vapor barrier will still be on the warm side of the insulation to deal with uh, water vapor trying to escape out through the wall. So the rain screen system really deals with water and water vapor trying to get in from the outside. It deals with the weather. So what does a rain screen look like? I'd like to show a few examples of rain screens. You do not need to remember these buildings, but it's helpful to be able to visualize the rain screen. And just to say that rain screens are not material specific. They can be built of any materials, and so we'll see a few examples of that. So this is a temporary kindergarten building in Switzerland, and you can see that it is wood construction. The exterior skin of the building is horizontal slatted wood, which looks a bit like a wooden fence. And you can see in the section below, it is wood stud framing with insulation between the studs. So if we look at it more closely, you can see now the open jointed outer rain screen in the photograph. Then behind that, you see in both the section drawing and the plan drawing below the airspace, then the sealed waterproof inner layer. So this is light wood frame construction. It is a stud wall. The area where you see parallel lines very closely spaced is the insulation. And then the innermost layer here is the plywood sheathing. So the plywood sheathing in this case, instead of being on the outside of the studs, is on the inside of the studs and becomes a visible interior finish in what is a temporary building. And so this is a model of that building, this open jointed outer skin, and the interior photograph showing the plywood sheathing as the interior finish. This is another project in Switzerland, which is a forestry service compound. So this provides an area for forestry workers to park vehicles and store equipment, and also to work in some enclosed offices. The image on the left shows the sheltered outdoor area where they park vehicles. And you can see that the horizontal slatted enclosure in this case is indeed a fence. You can also see that the columns here are tree trunks taken straight from the forest. So the trees are harvested, the branches are cut, the bark is stripped, and these are intentionally used to make a close conceptual relationship between the building and the forest. If we look at the two small buildings where the offices are located, you can see that this is a rain screen cladding system. So now the slatted wood outer layer is the rain screen, then there is an airspace behind, and then a waterproof backup layer. You can see here that the openings in the outer skin can run vertically or horizontally, and that the architects have also experimented with raw wood, and stained wood. So there are many aesthetic possibilities here. This is an example of a rain screen project, which is this is a small building in London next to an elevated railway. This was a leftover site that was very difficult to develop, and it's the kind of site that architects often purchase and develop themselves. So this is the office of architects DRMM in London. Their offices are at the ground level, and then there are two apartments above. The envelope system for this building is a rain screen. And you can see in both images that the architects have varied the spacing of the the open jointed outer layers so that the joints are narrower at the base of the building and then become wider as it moves up. At roof level, the open jointed outer layer then becomes the balustrade for the roof terrace. If we look at this more closely, it looks like it is a wood system, but it is not. This is cement board, which is imprinted with a wood texture and dyed. So it requires no maintenance over time. So you can see the open jointed outer layer. You can see the vertical metal battens to which the rain screen is clipped. This is what holds it in place. And then the light gray material behind is the waterproof backup layer. When we talked about the Stretto house, we did not talk about the cladding for the curvilinear zones of the house between the masonry bars. And you can see here that these curvilinear elements have extensive glazing and then a metal cladding system. The metal cladding system is a rain screen. And so these are aluminum panels, open jointed on the outer layer. If you read the drawing at the bottom of the image, starting at the very bottom, is the open jointed outer layer with the aluminum panels, then the air pressure equalization space behind. The dashed layer is the waterproof membrane, and the inner layer here then is metal stud construction with plywood sheathing on the outside and gypsum board as an interior finish. Rain screen systems can also be used for roofs. This is Kansai Airport in Japan by Renzo Piano, and the roof here is enormous, as you might imagine. This building that you see in the image is over a mile long, and it is an open-jointed stainless steel shingle system. So in the detail photograph on the left, at the top of the photo, you see the stainless steel shingles. These are open jointed, so this is the rain screen layer. You see the framing to which the rain screen is clipped or fixed, then the airspace below it, and then the corrugated metal at the bottom is the sealed inner waterproof layer. Uh, Roof terraces also often use rain screen systems. For example, you might have concrete or stone pavers, and these will be open jointed, so there's no mortar in the joints. And then there's an airspace below, and then the dark gray layer here is the waterproof membrane. And so what this begins to show, and this is also true of wall systems, is that the waterproof layer is hidden from view. And so it can be very efficient, and we don't have to worry about what it looks like. And the appearance of the building is then determined by the rain screen, which is the outermost layer. Then that's where we think about the appearance of the building. So this is an important move for architects. Let's look at an example of masonry rain screen. So if we return to our uh, thinking or conversation about the evolution of masonry construction, we remember that the cavity wall on the right represented a huge improvement over solid brick walls because it was better at keeping the water out. So the cavity wall is a kind of precursor to the rain screen wall. And indeed, it very nearly has all three layers of the rain screen. It has the outer withe of masonry, which is the brick withe in this photograph. Then it has the cavity or airspace behind, and it has the inner withe of masonry. The main difference between a cavity wall and a rain screen is that the outer layer of the cavity wall has sealed joints. It has mortar in the joints. So the cavity wall operates on the principle of the sealed system, trying to block all of the joints to keep the water out. It is not a rain screen. But we can do a rain screen with masonry. So this is a building in Paris called IRCAM. It's a music research center designed by Renzo Piano, and its exterior cladding is masonry rain screen. So in the drawing on the left, if we start from the outside at the far left of the image, you can see these are basically bricks or terracotta blocks, which are held in metal frames, and the joints are open jointed. There's no mortar in this outer layer. Then you see the airspace, the equalization chamber. The red dashed line is the waterproof membrane, and the sealed inner layer in this case is a steel framed construction with sheet materials for enclosure and interior finish. If we look at the cladding more closely, you can see the metal frame that holds the terracotta panels and to which the terracotta panels are clipped or fixed. You can see in the left-hand image that the dark lines are the actual open joints, and then the lighter horizontal lines are actually just recesses in the panel. So the dark lines are the open air spaces, and then we get the recessed lines. In the photograph on the right, this difference between the real open joint and the false joint is invisible. We can't perceive that difference visually. But you can see that this is an open jointed system, and this is the rain screen. The air moves freely through this outer layer. So on the left, you see the outer withe of a cavity wall, running bond, mortar in all the joints. This is a sealed system where we're trying to seal all the joints to keep the water out. On the right is the open jointed rain screen system in which air can move through the open joints to equalize the air pressure. So the rain screen sheds most of the water. It equalizes the air pressure. This is an image from the website of Boston Valley Terracotta, which is located just south of Buffalo. They're one of the leading manufacturers of terracotta cladding in the world. And this is their rain screen system. So you see the terracotta panels, and the joints between these panels are open. They have no mortar. You can also see that the joints between panels are shiplaps to deal with the issue of momentum. The metal framing behind is the system to which the rain screen is fixed, and that is also the airspace, the air pressure equalization chamber, and the gray layer is the waterproof membrane on the backup wall. Terracotta systems offer a lot of freedom. On the right, you see a system that is made with both flat-faced panels and curvilinear-faced panels, so there are a number of aesthetic possibilities here. This is an open-jointed rain screen system. And terracotta can also be used to provide sun shading for your building. So on the left, you see terracotta. These are called baguettes, like the loaves of bread that you buy. Terracotta baguettes held in metal frames. You can determine the spacing of the baguettes and you can vary the spacing. So with terracotta, you can get both a rain screen system and sun shading. If you were to use terracotta on your building, you would also earn points for LEED because you would be sourcing your materials in less than 500 miles from the building site. So you would be reducing the embodied energy on your project, in your cladding. So then if we review the three elements of the rain screen system again, starting from the left to the right, the outer layer is the rain screen. It is an open jointed system and it keeps most of the water out. It sheds most of the water. So we'll say 99% of the water is shed here. The second layer, where the yellow arrows are, is the air pressure equalization chamber. And so when air moves through the open joints, air pressure is equalized on both sides of the rain screen. So by the time we get to the waterproof inner layer, which is the third component, where you see the red dashed line is the waterproof membrane, we have only 1% of the water and very little or no air pressure differential to push that water or water vapor through any holes that are present. So this rain screen system improves both the performance of the wall and its appearance. By separating out the waterproof layer from the rain screen layer, we gain enormous freedom as architects. The waterproof layer is behind. It is not visible, it is concealed. The waterproof membrane can be very efficient, it can be very ugly, not presentable. And then the outermost layer, the rain screen, because it's open jointed, and we're not worried about keeping the water out with this layer. We have much more aesthetic freedom as architects. So this improves both the performance of the building, it gives us enormous freedom in determining the appearance of the building. The rain screen system is not a sealed system. It is an open jointed 3-layer system that deals with the force of air pressure differential to prevent leaks in buildings. Okay, that's it for today. Thank you very much.